Hi everybody, my name is Cameron and today we're going to be looking at structure and bonding. So we're going to be covering the three main types of bonding between elements. So our ionic, covalent and metallic, as well as the giant structures that those bonded atoms are then going to make. Okay, we're also going to be concentrating on the giant structures. So ionic lattices, okay, your giant covalent bonds such as your graphene, graphite, fullerenes, and as well as metals and metal alloys. So let's start off by looking at particle theory, specifically the states of matter. Okay, so we all know that there are three states of matter: there's solid, liquid, and gas. Okay, but what distinguishes those natures, or the state that these things are in? What's the difference between them? Okay, when we look at particle theory, it comes down to the amount of energy that the particles have in each state. Okay, so I like to think of water. Okay, again, this is a physical change. Okay, so no chemical changes are happening here. Water, as we know it, can be a solid, as ice. It can be a liquid, and it can be steam, as a gas. Okay, and you just have to remember that out of those three, which is going to have the most energy? It's going to be steam. Okay, and why? Because it's incredibly hot. Okay, that heat is heat energy between the particles. Whereas as a solid, ice is very cold. It doesn't have much energy, and that's why all of its particles are going to be tight together. Okay, in a very rigid structure as well, in a rigid form, which we can see here. So when we talk about the amount of energy that particles have, we also refer to their vibrations. Okay, so the more energy something has, the more it's going to vibrate and the more it's going to move around. And that's why gas is going to take up the shape and volume of the container it's in, whereas a solid is going to have a fixed volume. Okay, because those particles are not vibrating a lot. Add a bit more energy and those particles will vibrate more and eventually become a liquid, in which case they'll take the shape of the container that they're in, okay, while still being together. Give that more energy and they're going to start dispersing. They're going to start breaking off completely from the main mass. Okay, now the point at which something will go from a solid and get enough energy to become a liquid, we know it is the melting point. And for a liquid to get enough energy for particles to start leaving the main body is going to be called the boiling point. Okay, so when we're looking at different elements, we know that they are going to form different charges if they gain or lose electrons. Okay, but from our periodic table lesson, we also know that they are going to want a full outer shell. How they achieve that outer shell is going to make them a specific type of ion. Okay, so let's say we're talking about groups 1 to 3. Okay, groups 1 to 3 have 1, 2, and 3 electrons in their outermost shell. They're trying to get to a full electron shell. So it's easy for them to lose those electrons and gain the next to get to their previous outer shell's full shell. Okay, so if they had to lose their electrons to get to that, they're going to become positively charged. Okay, now when we say that they are positive ion because they've lost electrons, then we're going to call them cat ions. Cats are positive creatures in general. Okay, and when something has gained electrons to get a full outer shell, so such as group 5, 6, and 7, okay, we're going to call them anions. These are negatively charged ions because they have gained electrons. Electrons have a negative charge. Okay, I like to think of this as anions are like anonymous people online. If you ever look in YouTube videos or anything really where there's comments that can be anonymous, those people are usually quite negative. That's why they make themselves anonymous. Okay, so anions are negative, and that's when they have gained electrons. Okay, so just a quick recap on the periodic table. Let me get my laser. As we can see here, groups 1, 2, 3, and our transition metals as well are all going to find it easier to lose their outermost electrons and get a full shell of the previous shell than to gain those electrons. Okay, so it's easier for for all of these. Okay, because it's easier for it to just lose 1 electron than gain 7, or lose 2 electrons than gain 6. Okay, and so on and so forth. Whereas our groups 5, 6, 7, okay, it's easier for them, and our group 4 really, to gain electrons. Okay. Now remember as well, when it comes to ionic bonds, we're going to get to it. When I say gain, it can also mean to share. Okay. But when it comes to our metals, they like to give electrons. They do not share. It's important to know though that hydrogen, although it's on this side, okay, of the metals, it is not a metal. It doesn't act like a metal. It also wants to share electrons. And why is this? Because if hydrogen had to give up its 1 electron, it would be it would have no electrons. Okay, so it can be H plus, which is what we put it as, because it is going to be in our group 1. Okay, but usually it's going to be sharing electrons. Okay. Now when it comes to the interaction between atoms, there are 2 types of attractions. Okay, so we start out with having intramolecular attraction. So intramolecular attraction is between atoms. Okay, I like to remember that because intra-atom. Okay, so these are between atoms. This is it's due to their electrons interacting with one another. Okay. Intermolecular attraction is between molecules. Okay. So intermolecular, between molecules. And this is because after the bonding between atoms, you're going to have one side of this that might be charged. Okay, so hydrogen, once its 1 electron goes and bonds with that chlorine, all it has on this side is a positively charged nucleus. So that side of the molecule is going to be positive. Same thing with chlorine. Okay, on this side, all along the outside here, it's going to have all 7 of its electrons. So this side is going to be negative. And therefore, it's going to be attracted, but not with bonds like interacting electron bonds here, but just attracted between oppositely charged parts, we can say, of a molecule. So intermolecular attraction is between molecules. Intramolecular attraction is between atoms. Okay, so first type of bond that we're going to be looking at, this intramolecular attraction force, okay, is called an ionic bond. Now, a lot of my students get confused, or not confused, just mixed up between ionic and covalent. Okay, try break down the words. Don't try remember what they are. Okay, ionic, okay, means ions. So when we're talking about ions, what are they? Ions are charged atoms. Okay, so what type of atoms are going to be bonding with each other? Oppositely charged atoms. Okay, we're not going to have 2 positively charged ions being attracted and sharing electrons. That doesn't happen. Okay, for there to be ionic, it means they have to be oppositely charged. Now, what is oppositely charged? Metals and non-metals. Elements that want to give up their electron and other elements that want to receive an electron. This is what ionic bonds are. They are between metals and non-metals. Okay, it's going to create these charged ions because electron transfer and acceptance is happening. Okay, and that gives us these ions, these charged molecules. Okay, so some examples of these are like sodium chloride. Okay, sodium wants to give up 1 electron, chlorine needs 1. Once that transfer has happened, sodium becomes positive and chlorine becomes negative. Okay, magnesium oxide, calcium fluoride, all the same. Okay, I think that's meant to be calcium chloride, sorry. But yeah, it's just this transfer of electrons is ionic, creating charged ions. Okay, so the ionic bond is an intramolecular bond. Okay, now when you have these ionic bonded molecules now, okay, you're then going to have that attraction force between the polar, the oppositely charged atoms in that molecule with other molecules, okay, that are also going to be positively and negatively charged. This is called intermolecular forces. And these ionic bonded molecules are going to form what we call a lattice or a giant ionic bond. Okay, and this is when these molecules are going to be attracted to one another one's going to be attracted to another, and it builds this big lattice, this big sheet of interconnecting, intermolecular attraction between molecules. Okay, now these lattices are going to have certain characteristics because they are ionically bonded molecules. Okay, some of these are that they require a lot of energy to break the lattice, okay, because of how well attracted they are to one another. And if enough is applied, then it's going to become a liquid. Okay, so if you have something like a salt, okay, sodium chloride, let's say, that's an ionic bond. Okay, now salts themselves need a lot of energy to melt. Okay, your table salt, sodium chloride, needs something like 3,000 degrees of heat. This is Celsius as well, of heat to melt eventually. Okay, they have a very high melting point, let alone a very high boiling point. Okay, now these solid ionic compounds are not going to conduct electricity. They ask this in every test. Why is that? Why can they not conduct electricity when these ionic compounds are in a solid form? Okay, so to conduct electricity, you need electrons to move. Okay, now you would think, well, ions have moving electrons, right? They give electrons and they receive electrons, and that is true. But in a solid form, all of those electrons are bound. All of those electrons are interacting with one another, okay, and it cannot move. Now when we melt it, or if we put it in an aqueous solution using a specific solvent, okay, then it frees up those ions and they're able to interact with charged electrodes. Okay, so your cations are going to go to your cathode, anions are going to go to your anode. We'll get to that later, I believe, when we do electrolysis. But they have to be in liquid form, okay, because those ions need to be able to move. So in a solid form, there are no free ions to conduct a charge, to conduct that electricity, okay, whereas in the liquid or aqueous form, we just say the aqueous form rather, okay, because that can mean that either they're melted or that they are in a solution. Okay, then they are able to conduct electricity. Okay, so the next intramolecular bond or intramolecular attraction force that we're going to be looking at is covalent bonds. Okay, so these covalent bonds are going to be between non-metals. Now, is this something you should remember? No, it's something that you should understand. So covalent, I like to think of covalent as a co-op game. You know, you get these co-op multiplayer games. Now, what does co-op mean? Co-op means with your friends, right? You get some people and you're going to play the game together. You're going to share in the trauma of getting killed. Okay, so that's co-op. Co-op, covalent. They are sharing electrons. Okay, now what elements are going to want to share electrons? Well, certainly not metals. Metals don't even want their own electrons. They just want to give them away. Okay, but our non-metals, they're going to want to share because they're going to just want electrons. Okay, so they get together and they're going to share these electrons so that they can get both can get full outer shells. Okay, and that's what a covalent bond is. It's between non-metals that are sharing the electrons. Okay, so both are going to gain electrons to become more stable, so they're both going to be negatively charged, but they are sharing those electrons. Okay, some examples we can see here are like NH3, so ammonia, as well as our diatomic molecules, hydrogen, oxygens, chlorines, fluorines, okay, nitrogens even. They're going to be diatomic, they're going to be sharing electrons with one another. Okay, practice these dot and cross structures. Give yourself something like CO2 and go do it, and then go see if you got it right. Okay, it comes up in all the tests to draw a dot and cross structure, so it's good to get comfortable with it. Okay, the next one is also the ball and stick model. So a single line means that 2 electrons are being shared, one from each atom. Okay, double bond means there are 4 electrons being shared, so 2 from each. And then a triple bond is when 3 electrons are being shared from each, so that's 6 in total, which is going to be nitrogen. Okay, so go do some examples of this. If you still don't really understand how to do it or when to do it, book a class, okay, and we can go through it together. But covalent bonds are going to be the sharing of electrons to get a full outer shell between non-metals. So just like ionic bonds are going to have this intermolecular attraction that creates an ionic lattice, our covalent bonds are going to do the same thing. They'll also form these giant covalent structures. Okay, but although the actual covalent bond is extremely strong, okay, its intermolecular bonds are a lot weaker. Okay, and so the bigger the mass of the object, the stronger those intermolecular forces are going to be. And the main covalent, giant covalent bonds that we're going to be looking at are those of carbon. Okay, because carbon is able to link to 4 other carbon atoms, which will then further link to 4 carbon atoms, which further, and so on and so forth. Okay, and this can form these giant molecules, such as diamond, such as graphite, such as graphene, and we're going to be looking at it now. Because these molecules are going to get so big and big as it carries on building, the melting point and the melting point of it is going to be extremely high. Okay, so some of these giant covalent structures that we were talking about, again, intermolecular forces, okay, or intermolecular attraction, is that of carbon. Okay, so now carbon, as you can see behind me actually, needs 4 valence electrons to have a complete outer shell, or has 4 valence electrons. Okay, now depending on how many other carbons that one carbon is going to connect to, it will determine the properties of that giant structure. Okay, if that carbon connects with 4 other carbons, everything is stable. Okay, everything has a full amount of electrons. It has an exceptionally strong intermolecular force. Okay, and that forms a diamond. Now, diamonds cannot conduct electricity, but they have extremely high melting points. Okay, and they're very hard, they're very durable. Now, if that one carbon, okay, were to bond instead with 3 other carbons, it means that it has 1 electron that is unbonded and it delocalizes. Okay, now this, on the other hand, forms graphite. Graphite is what we find in our pencils. I know it's called lead, but it is not lead, it is carbon, specifically graphite with a bit of clay. Okay, so that's why graphite is able to conduct electricity, because of these delocalized electrons. It also creates these layers, okay, and that's why we're able to draw with graphite. Okay, it is leaving a layer of carbon on the piece of paper due to its bonding pairs, okay, or its bonding between 3 other carbons. So other than diamonds and graphite, carbon can also form a more 3D structure called a fullerene. Okay, now these fullerenes are characterized by these hollow tubes. So it can either be a ball shape like we see in this picture, or it can be a cylindrical shape. Okay, but these hollow tubes are called fullerenes. Okay, they're also just made up of carbon atoms. They have high tensile strength and they are used as reinforcing material. Okay, in biotechnology they can also be used to carry chemicals due to their hollow shape to a specific area. Okay, and finally the last structure we're going to be looking at is graphene. Now graphene is a single layer of graphite. Okay, they are still trying to figure it out in the lab and how to make it and how to use it, but it has a very low density and it's a very good thermal conductor. Okay, so the final bond, the final intramolecular bond we're going to be looking at is that of metals. So we've said that a metal and a non-metal coming together are going to form an ionic bond. We said that two non-metals coming together are going to be a covalent bond. Two metals coming together are going to form a metallic bond. Now what is a metallic bond exactly? And why does its structure allow it to conduct electricity so well? So when it comes to metals, they just want to give up their electrons. Okay? They don't want to share, they don't want to take it in. They go, I only have 3 electrons, I'm not going to gain 5 to get a full outer shell, just take them. That's exactly what they do. They go to another metal and say, hey, you want some electrons? And that metal goes, no, I don't want any of those electrons, let's just throw them away. And they both throw out their valence electrons. Okay. Now what this creates is a sea of delocalized electrons around these metallic or these metal elements. Okay, and it's that sea of electrons around them that allows them to conduct electricity so well. It also makes them quite malleable, okay, because of the spaces between these metal atoms. And I think in the next slide we talk about what happens with ores. Yes, so once we have these metallic bondings, okay, they can then form this giant metallic structure. Okay, these giant metallic structures again are able to conduct electricity because of the delocalized electrons, but they are also quite malleable. Malleable meaning that they can bend and move without breaking. Okay, but the issue is, or not issue, what can happen is if we form something called an alloy. Okay, now although metals can bend, which is great, sometimes we don't want them to bend. Okay, think of a gold ring. When you have gold, you have different carats of gold. Okay, and it's going to tell you something about the purity of the gold. Now it would be lovely to have 100% gold ring. Okay, but if I hit it anyway, it's going to dent, it's going to scratch, it's going to chip, it's going to bend. Okay, and we don't want that. We want it to be kind of hard. So what we're going to do is we're going to mix it with some other metals. Okay. I think with gold they put carbon in it. Think of steel rather. Okay. If I take iron, you can bend it. Okay. But if we add, okay, that also you add some carbon. But by adding these other atoms to it, okay, what happens is they are going to fill in the gaps between our metal atoms and prevent them from bending so easily. Okay, and this is going to form a harder substance. Okay, and it's going to be a mixture of metals. Okay, so an alloy isn't necessarily a chemical bond. Okay, it is just mixing them together.